So, good morning, friends. Today we are going to discuss about cantilever provided with UDL and point loads. So, friends, cantilever, it is a beam, so generally fixed in one position, and it is kept free at another position. So any beam, so which is fixed in one position and free at another position, it is referred to as a cantilever. Now, in any beam, several loads will be acting on the top of the beam, and these loads, they are classified into two categories. So the first one referred to as point load or concentrated load, and the second one referred to as uniformly distributed load, which is generally referred to as UDL. So point loads, they're called as PLs, and uniformly distributed loads, they are referred to as UDLs. So different loads will be acting, generally different loads will be acting at a different, portions or points in the beam. And basically these loads are classified into two categories, namely point loads and uniformly distributed loads. So now in this session we are going to discuss about a problem on cantilever, upon which point loads and uniformly distributed load are acting. So, therefore, this topic, it's generally it's named as cantilever with UDL and point loads. So, friends, this is the cantilever provided with one point load and one uniform distributed load. So, friends, we can see the arrangement of the cantilever. So, this is fixed at one end. It is fixed at left end of the beam. So it is called as a fixed end. So these hatched lines, they are used for indicating the fixed end of the beam. And finally, the right end of the beam, it is kept in free position. So therefore, it is called as free end of the beam. So this is the beam that is fixed at one end and free at another end. So that's why it is called as a cantilever. So now, friends, this fixed end point A is used for indicating the fixed end of the beam, and point E, it is used for indicating the free end of the beam. So friends, marking of points are very essential. So we have to divide the beam into several portions or regions, and we have to prepare shear force and bending moment equations for all these regions, and we have to select lower and upper limits for all the regions, and thereby we will be in a position to measure the values of shear forces and bending moments for the entire configuration. So therefore, generally, the beam, it is divided, all the beams, they are divided into several portions for writing SF and BM equations, and also for making SF and BM calculations. So friends, point A is used for indicating the fixed end of the beam, and point E, as shown in the figure, it is used for indicating the free end of the beam. And secondly, this is the point load. So that is given in the problem. It's also called as a concentrated load. So this is acting, according to the data given in the problem. So this point load, it is acting at the free end of the beam in downward direction. And the magnitude of this load, this is given as 50 kilonewtons. So generally loads are expressed either in terms of newtons or in terms of kilonewtons. But here in this problem, all the loads are expressed in terms of kilonewtons. So this is the way of representing a point load. It's also called as a concentrated load that is acting at the free end of the beam, and the magnitude of the load, it is given as 50 kilonewtons. So friends, this point loads, magnitudes of point loads, generally capital W is used for indicating the magnitudes of point loads, and small w, it is used for indicating the magnitudes of uniformly distributed loads. So as per the data given in the problem, capital W must be taken as 50 kilonewtons, and small w must be taken as 20 kilonewton per meter as given in the problem. So friends, capital W for indicating point loads acting on the beam, also called as a concentrated loads, and small w to be used for indicating uniformly distributed loads acting on the beam. So here, point load is given as 50 kilonewtons, and UDL is given as 20 kilonewton per meter. So therefore, capital W must be taken as 50 kilonewtons, and small w must be taken as 20 kilonewton per meter. So this is the way of indicating the magnitudes of point loads and uniformly distributed loads acting on the upper portion of the beam. And secondly, now here the entire load is concentrated at one particular point. So the entire magnitude of load is concentrated at one particular point, that is the free end of the beam. So therefore, it is referred to as a point load. Also, it is called as a concentrated load. So this is the point load that is acting at one particular point on the beam, that is free end of the beam, and capital E is used for representing the free end of the beam. So this is the definition, basic definition of this point load. So the entire load is acting at one particular point. It is called as a point load, and the entire load is, concentrated on one particular point. So therefore, it is also called as a concentrated load. So friends, point loads, they are also referred to as concentrated loads. Both the words convey the same name. And secondly, we can see the, uniformly distributed load. In addition to point load, one UDL is also acting on the surface of the beam. That is called as uniformly distributed load. So friends, as the name itself implies, the load is distributed uniformly for a length of 4 meters as shown in the given figure, or as shown in the given problem. So UDL is starting at the point B. So we can see the point B that is shown in the figure. Also, we can see one more point that is denoted by capital D. So point B, it is used for indicating the starting point of the uniformly distributed load, and point D for indicating the end point of the uniformly distributed load. So friends, starting from point B, this UDL, it is extending for a distance of 4 meters, and it is ending at point D. So this point used for indicating the beginning of UDL, and this is used for indicating the end point of the UDL. Now friends, this value is given as 20 kilonewton per meter. So that means it is acting at the rate of 20 kilonewton per meter. That means for 1 meter, it is exerting a force of 20 kilonewtons. And at this rate, for a distance of 4 meters, it will be exerting a load of 20 into 4, that is 80 kilonewtons. So at the rate of 20 kilonewtons per meter, it is covering a distance of 4 meters. It is acting for a distance of 4 meters. So therefore, 20 into 4, it will be coming to 80. So totally this UDL, it is exerting a load of 80 kilonewtons for a distance of 4 meter at the rate of 20 kilonewton per meter. So the load is distributed uniformly for this entire distance of 4 meters. So friends, that's why this is called as uniformly. That's why they are referred to as uniformly distributed loads. So if the entire load is acting at one particular point as shown here, so it is called as a point load or a concentrated load. And on the other hand, if the load is distributed uniformly for a certain distance on the surface of the beam, then it is called as uniformly distributed loads. So friends, this is the basic difference between point loads and uniformly distributed loads. And finally, as mentioned in the beginning of the class, capital W must be used for indicating the magnitudes of point loads or concentrated loads. And small w, it is used for representing the magnitudes of uniformly distributed loads. So friends, we have to realize the basic difference between point loads and uniformly distributed loads. And finally here, the beam is divided into, four portions. The first one, AB, for a distance of 2 meters, and BD for a distance of 4 meters, and DE for a distance of actually 2 meters. So therefore, the total length of the beam that is called as a span of the beam, so denoted by capital L, expressed in meters. So as per the data given in the problem, as shown in the figure, the total length of this beam, that means the total span or the entire span of the beam or total length of the beam, it is obviously it is given as 8 meters. So friends, capital L or small l is generally used for indicating the total length of a beam. So it is generally expressed in terms of meters. So as I've already told you, this is the starting point of UDL and this is the end point of the UDL. So the distance between fixed and starting point of the UDL is given as 2 meters. And the distance between end point of the UDL and free end of the beam, it's also given as 2 meters. And the distance covered by the UDL, it is given as 4 meters. So friends, different letters are used for marking different points. A for indicating the fixed end of the beam, and capital E, capital A for indicating fixed end of the beam, and capital E for indicating free end of the beam, and capital B for indicating the starting point of UDL, capital D for indicating the end point of the UDL. So the distance between AB is given as 2 meters, DE is given as 2 meters, and BD is middle portion. So UDL is acting in the middle portion of the beam. So BD, it is given as 4 meters. So totally the length of the beam is coming to 8 meters. So the total length of the beam is given as 8 meters. So AB is 2 meters, DE is again 2 meters, BD, it is given as 4 meters. So totally it will be the length of the beam will be coming to, 8 meters. And friends, one more point is given that is called as a point C. It is used for indicating the midpoint of the UDL. So UDL is commencing at point B and it is ending at point D. So naturally C is the midpoint of UDL. So that means this midpoint is 2 meters from the starting point, and also it is 2 meters from the end point of the UDL. So therefore, it can be taken as a midpoint. So capital C, it is used for indicating the midpoint of the UDL. So friends, AB is given as 2 meters, BC, it is also given as 2 meters. CD, it is shown as 2 meters. That means UDL totally it is acting for a distance of 4 meters. BD, that is shown as BD, that is given as 4 meters. And this distance DE, it is given as 2 meters. So totally this way, the length of the beam, it is given as 8 meters as shown in the problem, as shown in the figure. So sometimes we often get the problems on shear force and bending moment diagrams. So therefore, generally, figures are already given in the problem. If a figure is given in the problem, it's well and good. So based on this figure, we can divide the beam into different regions. We can frame SF and BM equations, and we can fix the limits and measure the values, and ultimately we can construct these diagrams. So the diagram that is already given in the question, that's already given in the problem, this is called as a loading diagram. So for indicating the various loads acting on the top surface of the beam. So it's used for indicating all the loads acting on the beam. So that's why it is called as a loading diagram. Now, using this diagram, we have to frame equations, fix the limits, and make the calculations, SFBM calculations. And finally, we have to construct these diagrams. And first one called as SF diagram, shear force diagram, indicating the shear forces at the various points on the beam. The second one called as bending moment diagram, so indicating the bending moments at various points on the beam. So friends, totally we have 3 diagrams. This is called as loading diagram. Second one called as shear force diagram. Last one referred to as a bending moment diagram. So loading diagrams will be given in problems. So using this data, we have to do calculations, and finally we have to construct shear force and bending moment diagrams. And finally, sometimes loading diagram will not be given in the problem. It will be given in the form of a description, 4 or 5 sentences. So one by one, we have to read, all the sentences. We have to understand the information given in the problem. So based on the information, sometimes we have to prepare a loading diagram before starting the problem. So if loading diagram is given in the problem, straight away we can start doing the problem. If it is not given in the problem, we have to read the problem, we have to understand the problem, and we have to prepare this loading diagram as per the information given in the problem. Then only you will be in a position to, start doing the problem. So friends, loading diagrams are very, very essential for solving the problem. If it is given in the problem, well and good. Otherwise, you have to read the problem, and after reading the problem, you must be in a position to construct this loading diagram also if it is not, given in the problem. So friends, some problems are provided with loading diagrams, well and good, and some problems are not provided with loading diagrams. So if loading diagram is not given in the problem, then we have to prepare this loading diagram. Then only you will be in a position to solve the problem. So friends, these are the things which we are supposed to remember. Now this loading diagram, the beam that is given in the loading diagram, it is divided into 4 components. It is not required for writing the equations. 3 portions are sufficient. The first one is AB portion, second one is BD portion, and third one is DE portion. So these portions are sufficient for preparing, shear force and bending moment, equations. So friends, finally, we have to start doing the problem. We have to start the problem from free end of the beam. We have to proceed in reverse direction, and finally we have to reach the fixed end of the beam. So this is the way of doing the problem. So for doing the problem, we don't need 4 portions. 3 portions are sufficient. One is AB, the other one is BD, and the last one is DE. So 3 portions are sufficient for preparing SF and BM equations. But we have to start from the free end of the beam. We have to proceed in reverse direction for reaching the fixed end of the beam. So therefore, DE portion has to be considered first for writing SF and BM equations. And secondly, we take BD portion. And finally, we can take AB portion for writing shear force and bending moment equations. So finally, let us note down the rules and let us make the calculations so far as this problem is concerned. And lastly, we can see the baselines. This is the baseline for SF diagram, and this is the baseline for bending moment diagram. So if you are getting positive values, so they should be shown above the baseline, and if you are getting negative values, they should be shown below the baseline. So in the case of SF and BM diagrams, positive values will be coming above the baseline and negative values will be coming below the baseline. So here we'll be getting all positive values, so they are coming above the baseline in the case of shear force diagram. In the case of bending moment diagram, we'll be getting negative values. They are shown below the baseline. So friends, baseline is very, very essential for constructing the SF and BM diagrams. Positive values to be plotted above the baseline and negative values to be plotted below the baseline. So friends, these are the general rules to be followed while constructing shear force and bending moment diagrams. So friends, let us make a review of all the things which we have seen so far. So we are dealing with a problem on cantilever. So this is fixed at one end, that is called as point A, and it is free at another end, that is called as point E, and the total length of the beam, that is called as span or span of the beam. Capital L for representing this parameter. So it is given as 8 meters in the problem. And secondly, we have talked about point load that is acting at the free end of the beam. So capital W must be used for indicating point loads, and small w must be used for indicating uniformly distributed loads. So therefore here point load is given as 50 kilonewtons. So capital W, it is taken as 50 kilonewtons. Uniformly distributed load, that is UDL, it is acting at the middle of the beam, middle of the span, for a distance of 4 meters at the rate of 20 kilonewton per meter. So small w has to be used for indicating UDL. So small w is given as 20 kilonewton per meter. And friends, UDL, both the loads are acting in downward direction. So positive signs must be allotted while preparing shear force equations. So it can be a point load or it can be an uniformly distributed load. So whether it is a point load or uniformly distributed load, the load that is acting in downward direction, so positive sign must be allotted for any load that is acting in downward direction. And secondly, friends, coming to these bending moments, now if a load is acting in downward direction, the beam will have a tendency to move in a clockwise direction. So always a negative sign must be allotted for clockwise movements while writing bending moment equations. So positive symbol to be used for writing SF equations, and negative symbol to be used for writing a bending moment equation. So friends, any force acting in downward direction, positive symbol must be allotted to a force acting in downward direction, and negative symbol to be allotted for clockwise movements. So these are the symbols to be used while preparing SF and BM equations. So instead of plus symbol, you are using minus symbol, and vice versa, you will be going wrong in the exam. So allocation of correct symbols, very, very essential while writing SF equations as well as bending moment equations. And friends, now finally point load. In the case of a point load, it is shown as it will be coming as a straight line in SF diagram. It will be coming as a linear line in the bending moment diagram. In the case of UDL, it will be coming in the form of a linear at SF diagram, and it will be coming in the form of a parabola at bending moment diagram. So friends, this is already shown here. So point load is acting in this region. So it is coming in the form of a straight line, and UDL is acting in this region, so it is coming in a linear form. SF diagram is coming in a linear form. And again, straight lines are coming in this region. So straight lines will be coming in the case of point loads, and linear lines will be coming in the form of, in the case of UDLs while preparing shear force diagrams. And similarly, in the case of bending moment diagram, so the variations will be linear in the case of point loads, and the variations will be in the form of a parabola in the case of uniformly distributed loads. So this is called as a straight line, this is called as a linear line, and again this is called as a straight line. So here we are getting linear straight lines or linear lines. So in the first portion and the last portion, UDL is acting in the middle portion. So therefore, it is coming in the form of a curve. So that is called as parabola. So friends, this is the way of drawing shear force and bending moment diagrams. So now, as usual, we have to begin the problem from free end of the beam and move in reverse direction before reaching the fixed end of the beam. So therefore, SF and BM diagrams must be written in this particular order. So friends, DE portion will be taken in the beginning, and afterwards we have to consider BD portion, and finally we have to consider AB portion for writing these equations. So friends, as I've already told you, always we have to begin at the free end of the beam, and we have to move in reverse direction. So this is therefore DE is taken as first portion. Now we have to consider a vertical section XX at a distance of X meter from free end of the beam. So here, if you look at the loading diagram, only one force is acting in downward direction. So in this portion, so SF it is given as 50 kilonewtons. Now this force is acting in downward direction. It is subjected to clockwise movement. So therefore, bending moment will be, it is nothing but shear force into perpendicular distance. So it is written as minus 50x. It's a clockwise movement. So therefore, it is written as minus 50x kilonewton meter. Now, friends, we have to fix the limits for this portion. Lower limit is taken as 0 meters, and upper limit will be equivalent to 2 meters. So this SF value is free, totally free of X parameter. So x is equivalent to 0. SF will be equivalent to 50 kilonewtons. And at X is equivalent to 2 meters. Also, it will be equivalent to 50 kilonewtons. And similarly, we can find out the values of bending moment. Substitute the value of X as 0. in this equation, bending moment will be coming to 0. To take the value of x as 2 meters in this equation, so it will be 50 into 2, so it will be coming to 100 kilonewton meter. So friends, these are the calculations as far as DE portion is concerned. So now we are coming to BD portion. So we are considering again for each and every portion we have to consider a section XX at a distance of X meter from the free end of the beam. So whether you are doing DE portion or BD portion or AB portion, this X meter must be taken from the free end of the beam. So in all the cases, it has to be taken as this section has to be taken at a distance of X meter from the free end of the beam. So friends, this is the basic thing which you are supposed to follow while preparing these equations. Now here SF, it is written as plus 50 kilonewtons. And coming to UDL is concerned, it is written as 20 into x minus 2. It is written as 20 into x minus 2. So that means you are considering a vertical section in this region at a distance of x meter from the free end. So this is 20, the magnitude is 20, and you have to remove this 2 meters from the total distance of x meter. So therefore it has to be written as 20 into x minus 2. So that's why, so this is point load is written as 50 and UDL it is written as 20 into x minus 2. And friends, coming to the bending moment equation, this will be equivalent to minus 50 into x, and this will be equivalent to minus 20 into x minus 2 whole square by 2. So it is written in this. That means we are taking 50% of this distance as a perpendicular distance. So force is equivalent to 20 into x minus 2. The distance must be taken as x minus 2 by 2. So therefore it is written in this fashion. And friends, now at x is equivalent to the lower limit is will be equivalent to 2 meters. The upper limit will be equivalent to 6 meters. So substitute the values in this equation. SF will be coming to 50 kilonewtons, and here it will be coming to 130 kilonewtons. The bending moment will be coming to minus 100 kilonewton meter, and here in the second case it will be coming to minus 460 kilonewton meters. So friends, wrongly it is mentioned as 460. By mistake, it has missed. This negative sign has mixed in this portion. So it is ultimately it will be coming to, it has to be written as minus 460 kilonewtons. So SF value is SF values, first value is 50 kilonewtons, second value is 130 kilonewtons. So, and similarly, first value of bending moment is minus 100 kilonewton meter, and the second value it is given as minus 460 kilonewton meter. So friends, this is how we have to make calculations in the second portion, that is BD portion. And now we are going to AB portion, and here also we have to consider a section XX at a distance of X meter from the free end of the beam. So now we have to write the shear force and bending moment equations. So shear force, it is written as 50 plus 20 into 4. So 50 is a point load acting in downward direction. So that means here we have to consider all the forces acting at the right hand side of the section from the free end of the beam. So point load will be coming into picture and UDL will be also coming into picture. The point load, it is taken as directly it is taken as a 50 kilonewtons. Now this UDL is converted into point load. So friends, for a distance of 1 meter, a load of 20 kilonewtons is acting for a distance of 1 meter. So for a distance of 4 meter, so a load of 80 kilonewtons will be, acting for a distance of 4 meters. So it is taken as 20 into 4, that is 80. So therefore, shear force will be coming to 130 kilonewtons. And we can write the bend. Secondly, we can write the bending moment equation. This is written as minus 50 into x, and this is written as minus 80 into x minus 4. That means coming back to this diagram, so it is converted into a point load that is acting at the center of this region. So you are considering a section at this point at a distance of x meter from the free end. So total distance is x meter, and this distance is equal to 4 meter. So therefore, this is finally it is written as 80 into x minus 4. So the magnitude of the load is 80 and the distance is to be taken as x minus 4 meter. So therefore it is written as 80 into x minus 4. So both these loads are acting in downward direction, resulting in clockwise movements. So we have to allocate a negative symbol for clockwise movements. So therefore negative symbol is shown for this value and also for this value. So it is written as minus 50x minus 80 into x minus 4. So friends, this is the way of preparing SF and BM equations for the final portion, that is AB portion of the cantilever. Now the lower limit should be fixed as 6 meter. That is, at a distance of 6 meter from B is a point B is at a distance of 6 meter from free end, and point A is at a distance of 8 meter from the free end. So this is lower limit is fixed as 6 meter and upper limit is fixed as 8 meter. So you substitute these values in these equations. So substitute the value of x in these equations. SF will be given as 130 and bending moment will be coming to minus 460. And take the value of x as 8 meters. Again, shear force will be coming to plus 130 and the bending moment will be coming to minus 720. So this is the way of dividing. So friends, we have to divide the beam into different portions. We have to start from the last portion at the free and proceed in reverse direction, reaching the first portion at the fixed end of the beam. So therefore, we have made calculations for DE portion, followed by BD portion, and followed by AB portion. So friends, we got all these values. They are plotted on SF and BM diagrams. So take the values of SF and bending moments. Take SF and BM values for all the portions and prepare these diagrams. But X is equivalent to 0. I mean, SF is plus 50 kilonewtons shown in this diagram. X is equivalent to 2 meters also. It is equivalent to 50 kilonewtons. And X is equivalent to 6 meter. It is obtained as 130 kilonewtons. So it is a linear variation. So it is coming to 130 kilonewtons. And at X is equivalent to 8. Again, it is 130 kilonewtons. It is coming in the form of a straight line. So friends, this is the way of preparing this, doing the construction of SF diagram. So these limits are fixed. We have fixed the limits for all the regions. We are starting at this point. So for DE portion, lower limit is taken as 0 meter. Lower limit of X is taken as 0 meter. Upper limit taken as 2 meter. For BD portion, lower limit will be equivalent to 2 meter. And upper limit will be equivalent to 2 plus 4, that is 6 meter. And for AB region, lower limit must be taken as 6 meter and upper limit must be taken as 8 meter. So friends, we have taken all these limits correctly in the previous slides. So for writing SF and VM equations for these portions. And we have taken the limits for all these regions, and we have measured the values of shear forces and bending moments. To take all the values of shear forces, prepare this diagram. That's called as a shear force diagram. Take all the values of bending moments and prepare this diagram. It is called as a bending moment diagram. Now, if you refer the values which we have obtained in the previous slides, so at X is equivalent to 0, we got BM value as 0, so this is shown as 0. At X is equivalent to 2 meters, it is obtained as minus 100, so this minus 100 is shown at this point. And at X is equivalent to 6 meter, it is obtained as minus 460 kilonewton meter. So we are marking, this has to be marked as minus 460. And friends, at X is equivalent to 8, that is at the last point, we got it as 720, minus 720. So minus 720 is marked at this point, that is the fixed end of the. So we got these values while doing calculations. First value is 0, and second value is minus 100. Third value is minus 460, and finally we got it as last value as 720. So we have to plot all these values in this diagram. So we are taking bending moment values and plotting this diagram. So it is called as a bending moment diagram. Now friends, as I've already told you, UDL is coming in the middle portion. So therefore, a curve is obtained in this middle portion. This is called as a parabola, and point loads are acting in these regions shown in the linear form. So this is a straight line in the form of a linear form, and this is also in the form of a linear form. So in the case of point loads, it will be in the form of linear. In the case of UDL regions, for UDL regions, it will be in the form of a parabola. So friends, these are the rules to be followed while constructing SF and DM diagrams. So we have discussed about this cantilever. So we have discussed about UDLs and point loads acting on cantilever. Also, we have discussed about the preparation, the construction of shear force and bending moment diagrams for cantilevers under the action of point loads and uniformly distributed loads. So friends, with this we are coming to the end of the session, and so here we can see about some information is given regarding construction of SF and BM diagrams. Take the values of SF at different points and construct the SF diagram. Similarly, take all the values of bending moments at different points, and we can construct bending moment diagram. So friends, we are coming to the end of the session. So thank you all for watching the session. Thank you so much.